Okay, we'll get started so we can end by 12:15 or earlier. So this hour is really for people who are interested in chemistry or in shock tubes or quantitative laser absorption to measure species in a time-varying environment. So I'll remind you about the laser absorption theory. I'll show you how sensitive these techniques can be if you're trying to think about how sensitively you can detect things. I'm going to show you a couple of different types of kinetics applications, and I'll talk about some new ideas. Actually, these slides are a little old, so we've done some newer work than that. But that's what I'm going to try to tell you now in the next hour. So remember, the governing equation is Beer's law because we're going to be using monochromatic light. Did I turn it on okay? Okay. We're going to be using monochromatic light, which means we can go ahead and use Beer's law for the fractional transmission at frequency nu in terms of the parameters we usually use: line strength, line shape, mole fraction, total static pressure, and length. So we assume a uniform distribution of properties across that length L, which we try to apply in our shock tube, where here's the length L, which is the diameter of the shock tube. So in principle, we have a laser. We usually split off a little bit of the beam to measure I0, because if there's any fluctuations here, we can null that out with our transmitted beam. There will be some losses across these windows, but they're fixed during the experiment, so we can take that out too. So line strength, line shape, and of course this is a reminder that we typically have some sort of a line shape, because most of the time this hour I'm going to be talking about species that have discrete spectra of individual lines, not the fuel example that I had earlier this morning. So in order to do this well, we have to have a quantitative database for S and P. So that's part of our work as we build this infrastructure. What species have been measured? So over time, and this is not the up-to-date list, but over the time I've been doing this at Stanford, we've probably done 20 plus different species using various combinations of ultraviolet, visible, and infrared. So infrared, those are rho vibrational. Ultraviolet, those are rho vibronic. These are mostly rho vibronic. So each species has its own absorption spectrum. So you'll notice I don't have hydrogen there, molecular hydrogen. I don't have nitrogen. But, and it looks like I have oxygen. So in order to do the diatomic molecules like oxygen, we can't use the infrared. We have to go to the UV. We could do nitrogen if we were to go to high enough temperatures. So we do the spectroscopy. We identify the spectrum maybe by reading, by calculating. We try to find the attractive transitions to use, and then we pick the line we want to use within the group of possibilities, matching it to the available wavelengths of light, and we do the line shape information. So we try to establish the absorption coefficient to better than 5%. So if we know the absorption coefficient is better than 5%, we might be able to measure the species accurately to about 5%. Better in some cases. To my knowledge, the first time a tunable laser, so I told you that we started to do this around 1970, which tells you how old I am. We started to do this around 1970. I was lucky, the lasers were just coming out. I had a chemistry office mate. He says, you should learn about lasers. Okay, so that was the turning point in my life, to begin to use lasers. And most of those lasers were fixed wavelength. You buy a laser and it's a special wavelength. But for scientists, you'd like to be able to tune the wavelength to places that you'd like to be. And so the first time we were able to do that was we did it in 1982 based upon the development of tunable dye lasers by chemists mostly. So we took these tunable dye lasers and we began to use them in a shock tube about 1981. And the first laser we used was called a Spectraphysics 380A. We still actually use one of these. This is what it looks like. It's a box that's about 1 meter long, and there's a pump laser. There's a source of light that's typically an argon ion laser in those days. The pulse of energy comes in, it excites a dye, a hydrocarbon dye. That dye then absorbs light and emits light. It emits it at a different wavelength range than the absorption, and then that's called the dye curve. And then within that range of possible wavelengths, you have an optical system which constrains the lasing to be in a narrow range. So you can, and then you can make it even narrower by using what's called a ring concept. So the laser jocks figured out a way to make wavelength tunable light available, which was a big deal for scientists. So that was, that's when that first happened in the shock tube anyway. It was around 1982, 81. Over time, we've used better and better lasers. Now we have this new mirror laser, Ti-Sapphire. So instead of using a dye, it's a solid state dye laser, in which the variable component is called titanium doped sapphire. So it still has the ability to vary the wavelength, but it's based upon a different gain medium. So that gave us higher power and better access to the UV over time. That was around 2009. Most recent lasers we've added is called the M squared UV Ti-Sapphire laser. Oops, back here. Okay, the UV Ti-Sapphire laser. So now this is a system that's maybe 2 meters long. There's the mirror in the background there. Actually, the mirror is back here. So these typically sit on optical tables, 8 feet long, in parallel with the shock tube. So we take the light out of one of these things and put it into the shock tube. Basically, this is what you have to do in the UV or the visible, or the short wavelength visible. Over here, we use diode lasers that are compact and small. You can see why I like them. We can access species that are different. These are combustion species. The lasers are much cheaper. You know, it's like a $300,000 laser. Not trivial to operate. So, but this is what you have to do if you want to make really good measurements of these species. So the lasers have evolved. The shock tubes have evolved slowly. The lasers have evolved faster. The detectors have evolved. Everything has evolved better and better. You might ask the question, well, what can you do? What can we detect? Having picked the wavelengths, how well can we do? So I've got two plots, I think, here. This is the plot of the minimum detectivity in parts per million. If we assume the gas is at 1 atmosphere, our shock tube diameter is 15 centimeters, and we have 1 microsecond time resolution. The noise always depends upon the bandwidth and the time resolution. Now, this is the spectroscopy. So up here, we have these curves, and you see that as you go up in temperature, the concentration detection limit goes down due to the fact that you have a declining Boltzmann fraction in the absorbing state. These are really quantum state-specific detections. So look at that. We can measure, say, 10 parts per million of CO2. If you're interested, and somebody's interested in the cool flames, NTC region, should have taken this down to 700 degrees. We can detect for CO2 maybe 5 parts per million or so, signal-noise ratio of 1. So when the molecules are bigger like this, the detection limits are poorer. Why? Because we've got more quantum states. So it's a combination of the Einstein coefficients and the fact there's more quantum states. But what if we go to diatomic molecules? OH is the one that we've just been looking at right here. So for the same conditions of path length, frequency, and I'm not sure, this is probably based upon our previous R17 work, not our new Q6 line. Probably could pick another factor of 2. But the point being that we can detect part per million levels of OH over the temperature range of interest in combustion. But you always lose ground with temperature because of the declining Boltzmann fraction in the absorbing state. The differences between OH, CH, and CN come in from the oscillator strengths. You may remember that I told you the oscillator strength for CN is 50 times better than OH. So there's approximately a factor of 50. CO. Now, CO, that is a rho vibrational. So you never do as the oscillator strengths for rho vibrational are always a lot worse than for rho vibronic. Anyway, you look at this and you say, wow, we can detect parts per million, tens of parts per million, if we have a reactor of this general type. So that's the attractive nature of this. And why do you care about this? If you want to do a chemistry experiment, the cleanest chemistry experiments are ones with the smallest amount of reactant. So the better the detection capability, the better the ultimate experiment you're going to be able to do. So ideally, you would work at part per million levels to minimize the influence of competing reactions and to minimize the difficulties of modeling the gas dynamics of the problem. So it's well, maybe tens of parts per million maybe 10 parts per million for CO, but it's sub-part per million for these diatomics. Okay, now, so we're interested in chemistry, at least I am. We talk about what's called the foundation fuel chemistry. So the ultimate behavior of hydrocarbon oxidation depends on the reactions of these smaller molecules. So for example here, this chemical reaction, OH plus H2. That's the one I'm going to show you as an example. So we really do, these are the things I'm going to show you. I'm going to show you foundation chemistry, meaning small molecule reactions. I'm going to show you some methyl esters because we're interested in biofuels. And then I'm going to show you how we might deal with slightly bigger molecules using isotopic substitution. So here's pictures. Here are pictures of our, I have 5 shock tubes now. This is a high pressure shock tube that can go up to about 1,000 atmospheres. Aerosol shock tube with the constrained reaction volume idea. Can't see it, but it's heated, a heated shock tube with long test times and so on. So we have 5, I have 5 shock tubes now. All right, so we want to talk about elementary reaction rates. Here are some of the reactions that are, if you do a sensitivity analysis and a calculation for some combustion problems, you'll find that these reactions appear often. So these are the reactions that we really want to nail down really well. These are some examples. And these are also reactions that we've studied at Stanford at various times over the last 30, 40 years. I'm going to show you 2 examples now of the red arrows. And that first one is the so-called branching reaction that's considered to be the most important reaction in combustion chemistry in terms of its impact on properties like ignition delay time. How do we measure an individual reactions rate? Well, we think about it. First of all, we think about it. We do some sensitivity analysis to design the mixture and isolate this reaction from its competitors. We use the shock wave as a means of step heating, and then we use laser absorption to detect species time histories. So I'm going to show you the example here for this important reaction. We've been working on this reaction for almost 30 years. 3 different students. Students typically take 5 years, but over a period of 30 years, we've worked on this project. So here's an experiment that this is not the most recent one. This is an experiment that was designed. So the variables in an experiment are the pressure, the temperature, the mixture, and the thing you measure. Those are the variables in setting an experiment. And you try to find the sweet spot where the thing you're going to measure is sensitive to the thing you want to know. So this is a case where at 1,400 and almost 1,500 Kelvin, 2 atmospheres, in excess of hydrogen, the student was clever and he designed a way that if he measured H2O, which seems counterintuitive because we don't have any H2O up here. If you measure H2O and do a sensitivity analysis, it says that over time in this experiment, the dominant influence on H2O history, that's like we've tried to optimize the experiment to be most sensitive to that and not much to anything else. Here's this experiment. Of course, this is after 6 months of making it better and better. He measures H2O versus time, and here it is. Here's this trace. And we've started with 1,000 parts per million of oxygen. We end up with 2,000 parts of H2O. So I'm feeling good about this. We've converted all the oxygen to H2O. And you can see that it's very sensitive to the rate coefficient we're trying to vary, K1. So we probably have determined this to within maybe 5%. So we think that this was a good strategy. So that experimental data set was green. My first student did this using OH laser absorption back around 1990. This is an Arrhenius plot in which you plot the semilog plot K versus 1 over T. We did this blue, and then the student came along in 2010, and we did the green, and then we came along with another method here, got the red. So the good news is all 3 of these studies line up really well, and they have much less scatter than the other alternative method called H-Eris. We're feeling pretty good about this. It's probably determined to maybe 5, 7, 10%. That's about as good as it ever gets. Here's the Arrhenius diagram. here's our best fit result. And we think, well, and the 1 sigma value is about 5%. So what's the conclusion? That using a laser rather than some other source of light leads to more consistent, low scatter results for this rate constant than possible before. Next example, OH plus H2. So one of my colleagues, Professor Hai Wang, said in his analysis of combustion and flame speeds, the next most important reaction that he wanted to know about was this one here, that the uncertainty in that existed due to past work was such that it was the dominant uncertainty in his flame speed calculations that he was using. There was the biggest uncertainty that he had at that time was in this rate coefficient, so we want to measure it. How do you measure OH plus H2? You can't buy a bottle of OH. Buy the bottle of H2. So anyway, we came up with a trick. We did not invent this, but it's a great trick. It's called the pseudo first order experiment, in which you put an excess of hydrogen together with a known amount of OH, a small amount of OH, and you watch it go away. This was really pioneered by people at Aerospace Corporation in California in 1984. They've also used it at Argonne National Laboratory. Shock tube experiments. Here's the idea. You start with something called tert butyl hydroperoxide. This is the structure of this molecule. And when it's heated to about 1,000 degrees or higher, it kind of instantaneously becomes this molecule, which is acetone, plus methyl, plus OH. So as long as these things are non-reactive, the only thing that will happen in our experiment is that OH will react with hydrogen. So in this case, we measure OH versus time in parts per million. Time behind the reflected shock wave, and you see the OH absorption goes from 0, jumps up to about 25 parts per million, 26, and it decays exponentially. Why does it decay exponentially? Because in this limit, the only reactions OH is the reaction and OH. Therefore, if that's the only reaction, and if the temperature is constant, it will be exponential. And that's called pseudo first order experiment. That's like the gold standard of doing experiments. No real temperature change, no real competition of reactions. High signal noise ratio. So you want to do this with the lowest concentration of reactants you can. And when you do this, we can fit it within maybe 3 to 5%. So here's our results for this OH plus H2 measurement. The idea is you put in a small amount of OH and a large amount of H2 so that the OH is predominantly removed by this reaction. And it flows only this way. So this leads to this small error bars and pretty good fit on an Arrhenius diagram. Those are two examples. We think the uncertainty is about 17%, the 2 sigma uncertainty. So you can see that when you do chemistry, it's really hard to get better than 10% uncertainty in a rate constant. But that's still better than the theoreticians can do. We compare these measurements that I just told you about in black with past knowledge. What you see is, well, we get good agreement, pretty much agreement with what existed before, but with much reduced uncertainty. And so Professor Hai Wang wanted this because he has to assign uncertainties to every reaction to get his overall uncertainty in the flame speed calculation. So by reducing the uncertainty, giving him a better value, a more accurate value, smaller uncertainties was what he wanted to improve the uncertainty in his flame speed calculations. So that's an example of trying to use lasers to study specific elementary reactions. Once they're known, once they're determined, that's it. You're not supposed to change them anymore, except within the range of uncertainties. I want to show you now some examples of methyl esters. These were really popular for biofuel people, these methyl esters. Try to use the same trick of using OH from T-butyl hydroperoxide, but with these different methyl esters, which have different sizes, different lengths. And I'm going to show you an example in which we looked at methyl formate, which is the simplest. This is the one with the smallest chemical structure. We're going to measure now multiple things and see if we can keep track of all the oxygen that's in the problem. So here's the methyl formate. Here's the methyl, and this is called the ester formation. You methyl acetate, so now we have something bigger out here, methyl propionate, and methyl side increases. The idea would be if we could measure these rate coefficients, we would understand how the chemistry changes with this structural change of just changing the chain. That was the idea. And what the student found is that if he did methylformate, is the black one here, and methylpropionate, is you make the molecule bigger and bigger, of course, then you have more places that the OH can attack this molecule. That all made a lot of sense. And the reason that the red one is down here is that there's a certain logic here of the way you expect the methyl acetate to be higher, but because the activity of the single H rather than the methyl. So basically, this is the state of the art for determining methyl esters plus OH. I think the scatter is about maybe conservative plus or minus 25%. Interestingly enough, when we did this was about 5 years ago. I was at Princeton, and I was talking to Emily Carter, who's now the dean here. She was calculating this, her student was calculating this. So this was a pretty big revelation that this was the state of the art of calculations then. This was the state of the experiment. So you can see they differ. This is what happens. A good experiment helps the theorists. And then the theorists and their models help us design our experiments. So everybody benefits. But that's about how well things were determined in that period of time. My point was that we need good quality experiments to make these. Okay, now I want to go to a specific case. This is methylformate. Here's the structure for methylformate. And this is what happens when we take another approach. Let's measure multiple things and see if we can test the chemical mechanism for longer times. So this is a case where we measure the decline of the methyl. Infrared laser to do that. Measure the formation of CO using a tunable diode laser. It's so good you think that it's a calculation, but it's actually data. We measure methanol using another infrared laser. We measure formaldehyde. It's a little harder to do, but it's down here. And we measure at the same wavelength as something that's either CH4 or CO2. And what do we find? We do this and ask, where is the oxygen? We're going to feel good if we can track all the oxygen. So here at 300 microseconds right here, we tracked up the added up these components, and we found 98% of the oxygen. That tells us we probably haven't neglected anything. Probably got this right. If you'd only measured one thing, you can't be sure, as sure as you can with this. That led me to really get interested in doing multi-species time histories. So rather than measure one thing, let's try to measure more things. Let's try to use atom balances and see if it's a tool for chemical modeling. Then we looked at, this is a time when we had an Energy Frontier Research Center led here by Princeton, actually, Professor Law. We were very interested in butanol as a target species for everybody in the team, of which about 10 professors. Here we have this normal butanol. Our strategy was to try to measure several things and see if we can build a picture of this. Now there's the different isomers of this tert butanol. There's different structures for this compound, so you have to kind of sort that out. There's multiple reaction sites and there's multiple isotopes. And so we use something called isotopic labeling. How do you deal with the fact that the OH can react? This is going to be OH plus butanol. How do we deal with the fact that it can react at different sites? How can we become site-specific? And so I won't spend much time on this, but the student was clever and figured out that we could use isotopic labeling so that we would buy tert butanol with different different isotopic labeling. You could buy O16 tert butanol, and you could ask what are the chemical pathways. And you're starting over here with this fuel, and OH can attack here, or it can attack one of these side structures. But unfortunately, if you track it down, you see that whereas there's multiple paths. And some of these paths reproduce OH. Now if I'm measuring the net OH change, I get a problem. Because some of the chemical paths actually give me back an OH. So I can't use OH time history without paying attention to this competition. But we dealt with this by thinking about it and modeling it, but then we dealt with it by, now let's imagine that we change this so that it's isotopically labeled, this thing now with 18. Now when you do O18, when that OH comes off, it doesn't compete with the O16. That's the concept. And with that thinking and with the combination of the thinking and the labeling and the measurements, we were able to sort this all out. In fact, and deal with this problem. Now that technique is being used by other groups around the world. Okay, so if we measure OH time history, we see with our tert-butanol idea, we see it rise, and it's the decline we care about, the rate of removal. We can see that we can fit this within about 20%. But that's when you do O16, meaning that it's not a fair measurement because some of the OH that's reacted comes back to you. So now we go to the trick and remove that removal, and you see that the OH removal, the net OH removal, once you've done the isotopic labeling, is different. So there's this difference in slopes that allows us to unravel the site-specific reaction of OH plus faster removal. So we could figure all this out and plot it on a diagram. And so typically what happens is there's multiple channels in reactions, and you have to try to unfold what fraction of the reaction goes one way or the other. So I'm just going to go over this fast. But so basically this was a big step forward, and the theorists come along real fast, and they start modeling this. Here's Sarathi from KAUST doing this in 2012. So as soon as you give them some good data, they can figure out a way to match it. So what I'm really showing you is that in some reactions, you got to worry about multiple paths, and some of those might affect your. So we did that. Okay, now we're always working to do things better. We're always trying to find a new species. I'm really interested in aldehydes, so I'd like to measure formaldehyde. This is acetaldehyde, propene, isobutene, acetylene. And we're always trying to make measurements more sensitive, and that's using this method called cavity-enhanced absorption spectroscopy. So aldehydes. The aldehydes are important in, say, the cool flame region or the first stage of ignition region. So the aldehydes are important. The two most important aldehydes would be formaldehyde and acetaldehyde. So this H is replaced by methyl. This is important about the first stage of ignition or oxidation, especially in oxygenated fuels. How do you measure those things? The challenge is that we couldn't find a wavelength at which absorbed only by one of these species. They're always overlapping. So we found that we had to use a trick. We would use multiple wavelengths. We would use some infrared absorption at about at this wavelength, this around here. So this is a plot of the acetaldehyde is in red, and the formaldehyde is in blue. So the point is they overlap. Because these molecules are big, they don't really have discrete line structure. Although formaldehyde over here in blue has features that are close to lines. So, but again, it's overlapped with acetaldehyde. So what do? Well, you look at this picture and you say, well, I can probably intelligently pick two colors, and two equations and two unknowns to sort this out. And that's really what we do. So we have to spend a long time on this, maybe 6 months or more. Actually use three colors. It looks like we use three colors. We use two in the infrared down here, and these two wavelengths are really close. And then we use one in the UV here. Try to pick it here so there's mostly the acetaldehyde. Then you pick over here and you try to find wavelengths for which there's some discrimination. So basically 3 equations, 2 unknowns, or 2 equations, 2 unknowns. So we have to check ourselves. We checked ourselves by building a known mixture of these things. We heated what's called trioxane and acetaldehyde mixture, and the trioxane decomposes to give you 3 formaldehydes. We watch the formaldehyde formation in this mixture under conditions where there is no other reactions, and we make sure we get the right answers when we sort out the these are the data. I just want to show you how the quality. So we do experiments at, looks like we actually tried 4 colors here. We used experiments at 4 different wavelengths. We look at the time history. There's the incident shock, reflected shock. You can see the time area variation of the formaldehyde and the acid. The reason I've listed 3 things here is all of these things are contributing to this blue signal. Some things contribute to the red signal, so that by varying the wavelengths, we can sort out the contributions of the players. And then if we reduce these data using our understanding, we can get back to what we want to see, which is that the acid aldehyde is here and unchanged. It just sits there. And the evolution of the formaldehyde that comes from the trioxane comes up and behaves just like it. Basically, we design an experiment, take into account the interference absorption, take into account the overlap of the species, and do multiple wavelength strategies to unfold. That's a successful story. Maybe took about a year. Now, I'm especially interested these days in jet fuels and hydrocarbon detection. So we're getting into how do we detect large molecules like propene, ethylene. These are all alkenes. And now that you'll notice that they're out here at, this is 10 microns. This is like 11 microns. We're out at long wavelengths where these big molecules all overlap. And that's a problem. And it's a real problem. How do we sort out individual species when multiple species absorb? Well, you do it by having more and more wavelengths of light and understanding the spectroscopy. Here's an example. This was the first time we detected isobutene. Butene, that's C4, 8, but it's a branched. And we produce the isobutene by heating isooctane and then watching the formation of the so you can, let's see, I'm losing track of what, these are 2 different temperatures. So if you do this at 1073 versus 1142, you can see how strongly temperature sensitive this reaction is. Go from isooctane to isobutene. So you start over here, and then you produce isobutene. So these reactions are extremely temperature sensitive, which reminds you why you have to be so careful about what is the temperature in your experiment. You can imagine if you start with isooctane, there's a lot of possible chemical paths. So the trick is to figure out what are they and how do we make them. We always frequently make comparisons with the Lawrence Livermore National Laboratory model. They're really into modeling large molecule behavior. When we made this comparison, this was the comparison between our data for isobutene and isooctane pyrolysis, and that's pretty good. Basically, what you can see is that at low temperatures, they're a little high, and at high temperatures, they're a little low. So there's something in there that's not quite right. And they can usually identify what they want to change. Pretty good agreement. Okay, now, acetylene is an important species if you're interested in soot formation or chemistry. It absorbs strongly at 3 microns up here, but it has a complicated structure. So we did this a few years ago. We're coming back to it now. When we did this a few years ago, we took the HyTran database and we calculated the spectrum. And we picked this wavelength for detecting the absorption. Now, my student who's working on this now tells me that he has found several lines that are missing in HyTran. When you go to higher temperatures, the HyTran database has left them out. You know, the database for hydrogen, for acetylene might be huge. So they have a cutoff. If the lines are lower than a certain strength, they leave them out. Yeah, but when you go to high temperatures, they become populated. So we frequently find lines that are missing in HyTran. Be careful about that. But we can detect sensitively acetylene. We went to propene, that's C3H6. We watched the decomposition at 1542 Kelvin, and we watched the formation of the acetylene. And that's the first time we've done that. And so the comparison with a mechanism called jet source from the University of Southern California is this. So what you see is that when you make a first measurement like this, it almost always differs from the model. the mechanisms are still evolving with time. And so we need data like this to guide the mechanism. Compare that then with Aramco is another, that's the Saudi Aramco, Housed, Science and Technology. But again, neither one of them actually agree with our experiment, and they don't agree with each other. So that's really the state of the art of modeling hydrocarbon reactions. It's an evolving science. And this is important if you want to model soot formation or pyrolysis of hydrocarbons. Okay, we're always trying to make measurements that are more sensitive, and so I'm going to finish up with something. I think this is the last subject. Called cavity-enhanced absorption. So remember when we have absorption, it's e to the minus k nu L. Well, what if you make L bigger than your experiment? What if you pass the light back and forth multiple times? Make L bigger. Then you can detect smaller amounts. And so this can be done by passing the light across back and forth a few times. But in a shock tube, when you pass the light in, typically through a window, when as it goes across, it's usually deflected a little bit by boundary layers. And so typically, in a multi-pass cell, what happens after a few passes is that you can't get the light back out of the... Typically, the mirrors will have an entrance hole, and everywhere else it's highly reflective. And they'll have an exit hole, and everywhere else are highly reflective. So you come in through the hole, bounce across a few times, and go out the exit hole. Well, by the time you've done 6 passes, it doesn't hit the hole anymore. We tried this so many times. We could not increase the sensitivity by increasing L. Every time we'd increase L by, say, 6, the noise would go up by 3, and we'd only gain a factor of 2, so it wasn't that helpful. But there's a new way to do this. The new way is, instead of trying to have the light go out an exit hole, use a mirror here that's coated completely that transmits, say, 1% of the light. So it's not a great mirror. It's a good mirror, but it's not a great mirror. That means that every time the light goes across, 1% goes out. And it goes back, and it comes back, and another percent comes out. But if you then, instead of using an exit hole, use this entire mirror, regardless of this beam steering that takes place, you can refocus it onto a detector. So you can get the benefits of multiple lengths by this trick. But it turns out that when you do this, you can't allow the successive beams to interact with each other, or you get what's called cavity noise. Instead of having the beam go retrace its stuff, you actually trace out a pattern so that the successive beams go different places. When you do that, you avoid what's called cavity noise. When you do that, you can get some pretty effective increases in length. And so it turns out that, roughly speaking, this is approximate, the effective length divided by the diameter, instead of it being 1, it goes as r over 1 minus r. So in other words, if r is 0.99, I can get a gain of 100 in path length. Now, it turns out that we actually don't want it to be much higher than 100 because it becomes so sensitive that we can't do an experiment that's clean enough. We had to deal with this cavity noise problem. And in doing this, we found out that this alignment was really easy. But you have to buy these mirrors. And then there's the question of, well, if you buy a mirror that's designed to be 9.99 reflectivity at your wavelength, it won't be 0.99 at other wavelengths. It's got to be. So you have to buy these mirrors, and they might cost $3,000, $4,000, $5,000. Then the question is, how long are they going to last inside the shock tube with all the stuff that's in there? That's a question. But we tried it, and it's pretty good. It's not perfect. In fact, most mirrors have held up. Some mirrors, after 6-9 months, we've had to replace. I'm going to show you then one example for carbon monoxide. Here's an example where we did an experiment at 4.6 microns, which is the strongest place to measure CO. We want to do an experiment where we know how much CO we should produce. So what if we put in 10 parts per million of acetone? Measure it at 1380 Kelvin. What should we get? If we wait long enough, we should get 10 parts per million of CO. So that's a controlled experiment. So we do this experiment in acetone, and we show that we can see the time history of the decomposition of acetone By looking at the final level, we realize we've got our calibrations just right. We're actually measuring parts per million versus time. By doing only 10 parts per million, it's nearly pure argon. It's as good an experiment as we can do. We also measure the pressure to make sure that it's constant for 1.5 milliseconds. So that's the first highly diluted CO formation experiment. Technically it was about 0.3 ppm. We only had 10 microsecond time resolution in this strategy. This is one advancement. It's a little harder than a single pass, but it's a way to get a gain of 10 to 100 or more in sensitivity. I'm at the end, almost at the end of this lecture, and I just want to point out, so a combination of, to me, a combination of laser absorption and shock tubes was like a frontier of combustion chemistry. We're at the edge where we can make contributions to knowledge. And so now I'm done with absorption. Absorption is my thing. But what about fluorescence? If you want to do imaging of gases, we got to go to fluorescence. If you want spatial resolution, so you keep saying, if you say, but how do I ever get spatial resolution? How can I ever study turbulent combustion? It's hard to use line of sight absorption. But fluorescence is absorption followed by emission. You're going to see the underlying basis of fluorescence is mostly the absorption. So I'm going to introduce to you tomorrow the simplest model for how we think about fluorescence. And slightly more complex models, I'm going to show you a bunch of applications. So if you're interested in spatially resolved measurements in an image in time, in instant time, PLAF we call it. That was invented in my laboratory. So absorption for line of sight, when you can use it, is the simplest, cheapest, best way to go, if it's uniform. Fluorescence is the way to go if you need spatial resolution, and you can still use a linear method. These linear methods would not let me measure nitrogen or hydrogen, so then you have to go to Raman. But so there are techniques other than absorption and fluorescence, but anyway, tomorrow I'll give you 3 lectures on fluorescence. Any questions? Yeah. Yeah.
I would assume that.
I think you're probably asking, is the chemistry of the isotopically labels? It is, I think, it is essentially the same. That's just all. Remember now, the isotopes don't change bond lengths. They don't really change bond strength. It just, so that's the key. As long as we can hold on to that idea, it's okay. The question is, chemists want to know, what's the relative rate coefficient for different places on the molecule? So, but if you're going to detect one thing, you got to be careful that you don't get it back. Okay. Any other questions? Okay, so we're maybe early a little bit. Let you go to lunch early. See you tomorrow.